I'm going to start with a little review of some of the things that we talked about before, for those of you who weren't here or don't remember. And then I'm just going to give a flavor of different kinds of quantum computing modalities that are out there, and some of the trade-offs associated with designing them. And then I'll conclude with a kind of a review of where things are at and what's available in terms of things you can access now. So who doesn't know what a qubit is? Everybody knows now? So the basic building block of a quantum computer, or at least one conceptual building block, is a quantum bit. It's the analog of a classical bit. Classically, you could have something that would be in two possible states, 0 or 1. And this is somewhat relevant, but classically also, you have to put in energy to switch the system from 0 to 1. And that's roughly, when we look at the scaling of the power requirements for our supercomputers, that's kind of the fundamental issue with, say, going beyond exascale, for example. This is so-called Dennard scaling, if you guys are familiar with that. Anyway, so there's a number of reasons why you might want to do something other than classical computing. One of them is if you could get rid of somehow that energy cost of flipping bits, then in principle, computing would be free or near free in terms of energy cost, at least. The other is quantum mechanics gives you this sort of crazy ability to potentially do computation on a space that's much larger than what you would be able to do classically. So the quantum analog of a bit, a qubit, can actually be in a superposition of 0 and 1. However you want to think about what that means is kind of up to you, but just mathematically, it means that we can essentially prepare the system controllably in an entire space of states between 0 and 1. In fact, it lives on the surface of a sphere. And that's a single element of a quantum computer, this quantum bit. And if you start adding them together, then the size of the space continues to grow. Sorry, before I get to that, what does it mean to do a computation on this? Classically, everybody, I think, is probably pretty familiar with the idea of a logical gate, and like an or an and or something like that. And that's how you build up a classical control circuit. That's how you build up classical logic. The analog is completely the same in the quantum case. You have quantum operations, quantum logic gates. And one way to visualize that is in the space of the sphere that I talked about, the surface of the sphere that represents the possible states of a quantum qubit or a qubit. I have operations that basically move me around in controllable ways. So for example, I could have a rotation around the x-axis. And I could go from being in the well-defined 0 state to now something which classically wouldn't have an analog, which is a superposition of 0 and 1 sitting on this y-axis. And I could also have operations that take me around this equator in various ways, and so on. Just like in classical computing, there's the notion of a universal machine, universal computing machine. So everybody's familiar, I guess, probably with Turing machine. It's a conceptual model which says, well, any classical computer can be mapped onto this. There might be some overhead, but essentially if I can do these basic operations, I can do all universal classical computation. There's a similar thing in the quantum case. So there's a minimum set of operations that you have to be able to do on this space. And if you can do that minimal set, then essentially what it amounts to is you can move to any point. You're guaranteed at some point to be able to move from any point in this space to any other point with a sequence of those basic operations. So the other thing that's sort of magical about these quantum systems, and again, this is review, is if I double the system, if I add 1 bit, I double the computational power in principle, with lots of caveats. But so, for example, classically, if you had 2 bits, you can represent a number from 0 to 3. That's the same with the quantum case, but now imagine those are the poles of this hypersphere. So there's not just the one sphere, which is this ability to have a superposition of 0 and 1. You can have a superposition of all possible states of those two quantum bits. So I now essentially have 4 parameters that are continuous variables that are required to describe the state of the system, but also are available as a computational resource. If I add one more, then I have 8. One more at 16, and so on. So 100 qubit quantum computer has a space to work with. It has dimensionality 2 to the 100th power. And that's sort of what gets people excited about, all other things aside, reasons why you might want to do this. Wow, I can just make 100 of these little qubit things, and I'll suddenly have this computational power that looks, at least on paper, beyond what I could do with CR or something like that in a reasonable amount of time. So the big issue here, and I'll get into this in some more detail, is that in order to have these kind of magical quantum properties, you have to be in the realm where quantum mechanics is describing the physical reality. And as we know, sitting here in a 300 roughly Kelvin room, there aren't really many superpositions going on between us large macroscopic objects sitting here. So just to say, our daily experience tells us that classical mechanics is the rule of the day. And you really only encounter these exotic properties of quantum systems when you have very small, isolated, cold systems. And essentially, what that amounts to, this is, again, a bit of a digression, but an atom is quantum mechanical, right? You can have different energy levels in there, and in fact, that's one of the methods used for building quantum computers. You store the information in the state of an individual atom. But that atom is seeing, even an isolated atom, it's seeing the vacuum, which means that it can decay from some excited state and emit a photon, basically at random. Now, for a typical isolated atom, that's a pretty rare process. But it's an indicator of the broader thing, which is that it's essentially impossible to build a perfectly isolated system. So no quantum system is really a pure quantum system. They're all open. They're all coupled to the outside world in some way. And that coupling basically allows classicality to seep in at some rate, which means that I ideally produce these states that are superpositions of and live in this super high dimensional space. But what the rest of the universe is conspiring to do is force that to collapse into a single representation of a classical number. So like in that, in this case, I have this all possible numbers between 0 and 4, or between 0 and 3. Interacting with the classical environment just a little bit will basically project the system into just one of these choices. And so what I'm left then is with just the classical information. So in designing a quantum computer, that's in some sense the fundamental challenge. Dealing with the fact that you have to control the system in order to get it to do your computation, but you also can't allow it to see the outside world, at least in an uncontrolled way. Uh-oh. That's kind of oh, exciting. All right. Apologize. I didn't do that on purpose. So I sort of presented something similar to this in the thing about quantum devices. What is a quantum device? I'm just restating what I said out loud a minute ago. You've got some quantum system, and a lot of times when people talk about quantum computers and quantum this and that, there's a lot of focus on this object. This is supposed to be an atom, by the way. It's got a positive and negative part, electron. And it's quantum, it's magical, and so on. But in order to actually use it, I have to control it. In order to control it, I have to couple to it. So that control is coming from plain old vanilla classical electronics, photonics, whatever, some classical source. And this is a little tongue-in-cheek, but I put NIF on here as my classical source. It's kind of a joke, but the point is that this is a serious component of the problem. There's lots of atoms in the world, right? There's a lot in this room, and so hey, why don't we have a really big quantum computer here? Well, it's because we don't have the infrastructure to go in and control that individually in a controlled way. Then on top of that, as I'll get into a little later, it's not enough to have the electronics and the sources and nice, clean, pure tones to control the system. There's actually a fair amount of classical computing that's required in practice for realizing a universal quantum computer, and that's basically to correct these errors as they occur. I'll get to that at the very end. The other thing here is that I'm drawing an electromagnetic wave because I'm struggling to think. I can't think of a single system that's been proposed as the physical realization of a quantum system that essentially isn't being probed, manipulated by EM. So there may be, maybe there's a strong or a weak force version or something like that, right? But all these things are effectively, even neutral systems, they're ultimately coupled to with EM. And so this is kind of a photonics problem, or if you're at lower frequency, it's an RF problem. But that's a fundamental component to this. And the EM characteristic of this also is important also in the sense that probably those of you who took classical E&M, you know that the Coulomb interaction is long range, which it's fundamentally long range in the sense that it doesn't normalize away. I can go out to near infinity between two spins, two electrons, and I can still see the effective force. That means that this notion of building isolated components, and then I say, okay, now, and I'm going to use EM to couple to them, has some fundamental sort of paradoxical character to it. All right, and so this is again kind of, I like this slide, so I'm reusing it from last time. This is my could be my quantum sensor, my quantum computer, whatever. This is where all the magic happens. And the point of this is to give a flavor of the extreme length and energy scales associated with this coupling of this quantum system with that control infrastructure that I mentioned. So typically, it's not necessary, but typically you're going to be operating all this stuff at room temperature. It's going to be separated from the actual quantum system by probably meters. And then the quantum system itself, it could be a nuclear spin. That would be pretty small. It could be a single atom. That's a little bigger, still pretty small compared to a meter, and so on. You kind of get the idea of the scale of the quantum system you're trying to manipulate, tiny, let's say nanometers or less, and then the scale of everything I'm using, the sledgehammers I'm using to try to control this thing, is on the order of, regular junk. The other thing is just these energy scales. So a big part, and I'm not going to get into this in really much detail, but you have to do a lot of work to isolate this system from the environment, even though you're doing this control. So almost inevitably that involves cryogenics. Could be relatively extreme cryogenics, high vacuum. You've got materials issues where you're trying to deal with energy transport over very large length scales, very large energy scales. So that's challenging. And then standard things, shielding and so on. And as I'll get into a little bit later, there's pretty extreme requirements on these classical elements too. And in some cases, we don't have the classical equipment. We don't have the compute power or the speed to realize what we would need in principle to realize universal quantum computation. All right, so now moving on from the review, this is it. This is the answer. How do you build a quantum computer? I think everyone we'll pretty much be ready after this talk to go do that. So the step one, which gets a lot of attention, is what's the quantum system? So let's choose the quantum system. And people say, well, what kind of quantum computer are you building? Is it an ion system or superconducting? Or, well, we're doing quantum dots or this kind of thing. From my perspective, that's in some sense the least difficult, the easiest part. Although it all comes together. I mean, the choice you make here obviously impacts everything else. But to give you some idea of some of the choices here, you can use, as your fundamental object, you can use photons to store your quantum information, and then you need something to be able to manipulate those photons. So that's essentially actually what superconducting circuits are doing. Your quantum information is being stored in the states of electromagnetic excitations. They're in the RF regime. They're still photons. So you often see people say, well, hey, we're not doing this lousy superconducting stuff or ions or whatever. We're doing photonic quantum computing because it's amazing and photons don't interact with anything. Well, if they don't interact with anything, you can't do anything with them. So that's just an aside. So in general, there's other things. So I'm just kind of drawing these into two categories. One are things you build. They probably look at some level like a circuit or a regular. There's a component that's a fabrication challenge. So there's quantum dots. There's defect centers like NV centers. Maybe some of you have heard of NV centers. There's even notions of sort of engineering exotic flavors of materials that have topological protection from their condensed matter properties. Then you have the sort of other camp which says, hey, I don't want to build these things. I mean, I want the object that I'm controlling, this quantum object, to be as reproducible and manufacturable as possible. And so a pretty good option there is an atom, because they're pretty similar, right? So if you have one, you know what it does, you know what another one does. Some neutron counts aside. But so that's a really good choice. And then you could even say, hey, why bother with that atom stuff? I'll just use single electrons. People are interested in that. And then you could, again, look at go into the nucleus and use the nuclear spin. There's a lot of value in this track. The issue associated with why you would choose one of these over the other amounts to all the rest of this, which is, well, nuclear spin, very isolated. It's going to stay in a quantum state for a very long time, but it's very isolated, and so it's very hard to control. And if I need to have I need to basically have very high field strengths in order to do anything with a nuclear spin. If any of you had an NMR, you go in there and you hear the clicking and all that kind of stuff, and you're not supposed to have the metal implant when you go in the room because the field strengths are so large required to extract that information from the nuclear spin. Now, if you think of, hey, I'm going to use that for computation, you maybe can kind of see some of the challenges of bridging those lengths and energy scales in that kind of case. Okay, so then number two, step two, you've picked your thing, you're going to just store your information in, and now all you have to do is isolate it from the environment. And depending on what you choose here, this may or may not be easy or hard. Like I said, a nuclear spin, I choose that, and it's pretty isolated, even at room temperature. But it's hard to control. On the other hand, if I say I'm going to use superconducting circuits, well, I obviously need to be cold enough to have superconductivity to work, this kind of thing. So when you choose these things, there's an energy scale that you're choosing. There's an effective inherent coupling to the outside world that you're choosing. And there's this trade-off of space where if it's easy to control, easy to, say, flexible in terms of how I'm going to put it together and design it, I'm essentially already deciding that it's going to be, there's going to be a challenge associated with isolating it from the environment. And then the final thing, which is sort of in some way beyond hard, is, oh yeah, by the way, I need to be able to control this in a reliable and reproducible way. and I think it's, well, it could be overemphasized, but I don't think I'm overemphasizing it at the moment. The sort of paradox of this system needs to be completely isolated from the classical world in order for it to be quantum, and yet I'm claiming I'm going to control it from the classical world. So there's a bit of a disconnect, right? Give me something here. Yeah. All right. So. Yeah, so you have to provide these control signals. You have to measure the quantum system, and then in some sense, the most stringent piece here is you have to be able to apply feedback, and you have to be able to apply feedback on a time scale that's relevant to, say, the decoherence of the quantum system. And I'll get into all of those things in a little bit. Now, getting to these questions of coupling and control, it's not enough to be able to control a single qubit, because remember I said there are these universal set of operations that are required. Some of them are rotations on a single qubit. That would be like flipping a single bit. But you can't build a classical computer if all you can do is flip single bits. You need at least something like an exclusive OR or an AND or something like that, so that the state of this bit affects the state of the other one. Right? It's the same in the quantum case. And that means that it's not enough to have a bunch of isolated quantum systems that I can control individually. I have to controllably go in and couple at minimum, individual pairs of those objects. And that already introduces major constraints on how you're going to lay these objects out, how you're going to couple to them and get your signals in, and so on. So this is sort of two potential paradigms. One is, here's my quantum bit. It can be in this superposition. And now I basically run a wire to a classical controller, just to that guy. And then maybe I multiplex something that on that same line that allows for an effective coupling between these guys. If you imagine what that looks like in terms of wires, and you want to do that in a planar system, that's hard. Those of you with maybe a little bit of math background know that, in fact, if there's if you have more than 4 nearest neighbors, there's actually no way to do that in one plane. You have to basically have one wire crossing another and this kind of thing. And now, if you imagine that those wires are supposed to control something and they're not supposed to see each other, because if the signals in the different wires see each other, then that's going to make the control scrambled. That becomes a difficult challenge. The other direction would be, all right, everything's going to see everything all the time. Well, that might be a good solution at some level, but in order to understand the evolution of that now many-body quantum system, I have to have solved for the quantum evolution of the many-body system classically in order to know what control signal to send in to get it to evolve in that way. And gosh, that turns out to be an exponentially hard problem. So this is another one of these kind of trade-offs. You make a choice about what you're going to choose for these objects, but you're not done, because you have to figure out how you're going to get them to couple together, how you're going to send in controls to be able to do addressability of all of them. All right, so now for something completely different, I'm going to talk about specific implementations. And I'll focus on two. One is ion traps and the other is superconducting. And that's mainly because those are the sort of dominant avenues that people are pursuing, at least at the moment, for trying to realize quantum computers. They look pretty different on the outset, but then when you kind of step back, they both are suffering from many of the same challenges. And it all goes back to kind of those trade-offs I was talking about earlier. So here's what you're looking at here is a chain of individual atoms. It's pretty cool that you can actually do this. You have individual atoms, you heat them up, you collect them, you cool them with lasers, you get them to line up, and you construct an electromagnetic trap that forces them to be sitting in a well-defined potential. And then you can go in and individually probe them with lasers, get them to essentially emit if they're in one state or not emit if they're in another state. And so you can measure and control them. And all right, great, we have a quantum computer. What you're looking at here is sort of layer one of one version of how you get that sort of everything else and to have this beautiful chain of ions. This is basically an electromagnetic trap. It's been constructed using standard fabrication techniques. The big challenge there is you're sending in huge RF and static potentials to construct this artificial potential so that the ions can float above the surface of the trap and be manipulated, but at the same time not see the environment and so on. So this here is a vacuum chamber that would be closed up, pumped down, and that's enough to get them to be pretty isolated from the environment. You don't really have to cool the system that much, although if you start looking at the details, the way that the coupling occurs between these individual ions is through a very weak, so if you, let's say you excite one of the ions and you put it into an excited state, it gets a little bit of a momentum kick when you do that. And that momentum kick, since this is in a trap, allows the motion of the internal state, the electronic state of the ion, to be coupled to the motion of that ion. And since they all see each other through this Coulomb interaction, everybody sees that. And so you have the internal state, the individual qubit, that's being mediated just by this wonderful, reproducible, well-protected internal electronic state. But then in order to get them to couple together, I'm basically doing Newton's cradle, or I'm forcing them to excite actual macroscopic vibrations of this chain. And in order to, say, couple this ion to this ion, I need to excite a mode in that system where only those two ions see each other and the other ones don't. If you've ever thought about, if you studied what happens with a string, of course there's a fundamental mode for a string, and then there's higher modes and so on. As this gets longer, the number of vibrational states that are allowed blows up, and they start getting scrambled with each other. And so it becomes very difficult if this chain gets too long for you to controllably couple, say, this guy to some other individual one in the end. So some of the routes for getting around that, well, okay, we can't build this by just making an infinitely long chain of these. I'm going to design a surface, I'm going to design a trap where I can actually shuttle around individual ions. So I'm going to put an ion here, I'll put it in some state, and then I want it to interact with that guy, so I'm going to route it over and then get them to interact. You can actually do this, which is just, in some way, it's beautiful, it's nuts. You're really shuttling around individual atoms. But on the other hand, it's kind of stupid, right? I mean, as an element of a computer, if I need to basically have the individual bits in my computer, I need to physically route them around and get them to interact. That's a challenge. But the origin of that challenge is sort of fundamentally, I'm sort of beating this horse. It comes down to this trade-off that we made in terms of deciding how we were going to couple to these individually and how we were going to get them to talk to each other. Then, so beyond that, usually I didn't actually get into this, but how many qubits do people think you need to do something interesting? So in the very beginning, I said, well, 100. That wouldn't be very many classical bits, but it's quite a few quantum bits if I could actually use them all, because of this 2 to the 100 size space that we're dealing with. It turns out that, sort of jumping the gun a little bit, because these things are coupled to the environment and they decay, the quantum states decay, you have to be constantly correcting errors. And in order to correct errors, the simplest way is to sort of duplicate resources. That's how you do it classically. Like if you have a, let's say you have some bit stream and there's a probability that one of your bits will flip. The simplest thing is to double your data, right, and then vote, or triple your data and vote. You know, use 3 bits instead of 1, and if one of them flips, you're like, hey, these 2 are still up, so I'm going to call that a 1. You can do the analog of that in a quantum system. It requires more qubits. It requires larger quantum resource in order to accommodate for that sort of overloading. And then the number that you need, the number of resources you need in order to correct errors is a function of that error rate. So depending on what system you're looking at, you could need an overhead of, say, 10,000 qubits to realize one, what would be called logical qubit, which would be, I've now done all the error correction so that I can essentially suppress errors to some point where I can completely ignore them. And now, but I built a system with, say, 10,000 atoms, and I'm getting the equivalent of 1 out of that without errors. And then if I want 100, okay, now I need 10 million. So that's a lot more than 100. So then people start thinking about, okay, well, how am I going to scale this? And you end up getting things like this, which are pretty notional. I'm going to make an elementary logical unit, right? And now I'm going to couple them together with some kind of a bus. Here, the physics behind this is you're actually going to take the information that's stored in individual atoms and devise a way to get that information and turn it into the state of a photon, say the polarization of the state of a photon. That photon goes around somewhere, I route it, then I use that measurement of that to then impose its quantum state on another ion in some other system. And as crazy as that sounds, that's actually been demonstrated at again, at sort of a demonstration level. And so that's the notional way that you might build up something like this. You turn what was a localized quantum state into a flying photon that's encoded that quantum information, and then you recover that. And the challenge there is what you might imagine is, well, what's the efficiency of that process? It's pretty low. And so now you're talking about even more resources piled on to overcome the fact that scaling solution is imposing additional inefficiencies. All right, so moving on. Another nice way to think about where to store your quantum information is in the excitations of a quantum circuit. So what you're looking at here is a planar circuit. I know when I first encountered RF circuits, it was really mysterious to me. You know, all these squiggles, it doesn't look like. Who like intuitively understands RF circuits? Well, this is one way of looking at this. This is basically an inductor. Remember the squiggle that you draw when, you know? So that's what this is. It's an inductor. It also has a little bit of capacitance. So it turns out that this little squiggle, which is basically a superconducting wire on a substrate, is an oscillator. It's got an inductance and a capacitance. So it's an LC oscillator. These objects are also actually LC oscillators, and they have the little special ingredient, which is this Josephson junction. I'm going to skip the explanation of what that is, but it gives you, it's the reason why superconducting systems are a great way to do photonic quantum computing. They give you a nonlinearity for free, which is sort of like, if those of you are familiar with optics and quantum optics, it's giving you a lossless photon-photon interaction. And that's, remember I said, hey, photons are great, but if you can't get them to interact, then you can't compute with them. So the reason why superconducting systems are popular and at the moment a good candidate for doing some of this is you have this sort of quirk of quantum mechanics, associated with this object called a Josephson junction that allows you to make photons that are trapped in this circuit to interact with each other in a strong way at levels that are much higher than any other nonlinear optical process. So here you've got 4 squiggly oscillators connecting these other oscillators. And so these are your qubits. This is how the qubits are coupled to each other, and this is how you control and measure the qubits. And this is a good image to look at in terms of when I was talking about the connectivity. Imagine instead of having 4 of these, now I want to have 100 or 10 million. Routing all these squiggles to these little things is going to be a problem. So another nice thing about the superconducting systems, though, is that we actually are talking about photons. So I can trap those photons however I like. I don't have to trap them in a wire. I can trap them in a superconducting cavity. And so you have the freedom to go to a 3D geometry, and you have the freedom now to manipulate the signals that you're using to drive this in 3-dimensional space. The fabrication is completely different from what you would do for a conventional circuit, because now I have to care about actual large scales in 3 dimensions. On the other hand, maybe it's simpler because I can machine this on a mill, and this is not that hard to do. Then the chip part is trivial relative to what I would need for like a typical semiconductor kind of process. So the point here is that there are a lot of ways to do it, lots and lots. Okay, lots of ways to use this resource, and they're essentially just scratch the surface is where we're at with using that as a resource. One other note is you can couple these systems with other things. So here's a really cool paper from Yale where I've got that same this 3D transmon. Oh, by the way, this isn't just it looks. Those of you who are experts in RF, this is a dipole antenna, right? It's just 2 blobs, and then there's a little junction here, and that's your quantum bit. Pretty simple. And that dipole antenna is now coupling to the electromagnetic mode in the cavity. So it really is. So here's a similar system. We've got that same dipole, and now you've put a little piezoelectric material on top of one of those electrodes. And so when your electrons or Cooper pairs are sloshing back and forth in the excited state of this antenna, they actually are deforming the material a little bit. That deformation is producing vibrations, and those vibrations are quantized. And so you can actually transmit your quantum information that was in a photon into a phonon, which is just a quantized vibration of the material. Kind of neat. You could do this with any number of things, and there are a lot of schemes where people are kind of say, hey, I'm going to take the best of all worlds. I'm going to use ions for storing this because they're great, and then I'm going to use superconductors to control them because they're great, and I'm going to put them all together, and that's my quantum computer. And I think there's nothing fundamentally wrong with that. But what you find in practice is that instead of getting the best of all worlds, you get the worst. You get the worst qualities of all of them jammed together into one system. But that's also just a reflection of the kind of immaturity of the field and the room we have to grow. So, all right, how do you scale this up? Well, at some level, and I would say naive level, it looks easier than the ion case because we know how to scale transistors. We know how to make chips with lots and lots of things on them reliably and so on. And so what you see from most of the industry players in the space is following that path. The idea then is here's one quantum object, you're going to have some coupling, here's another one. And so you're making a lattice of some kind. You're going to get the performance of one lattice unit cell to work, and then just scale it up. could work. But again, the devil is in some senses in the details of, oh, well, how was that? Remember we said, like, in this picture, each one of these qubits needs a control line. So I'm going to want to control this qubit. That means I need to have a multi-layer process. I need to have routed the control somewhere under the surface, brought it up, and had it interact with that without messing up any of these other things. This is an area where, to me, there's an opportunity, and the lab is doing some work in this space, of going to look at advanced manufacturing methods. So we can open up that third dimension. You know, maybe we could actually use additive manufacturing to build quantum computers, which I think would be pretty cool. This is now the other piece of this. I didn't have this detail slide for the ion trap, but the ion trap, it needs a vacuum. The piece that we're not showing is the lasers. So each one of those ions, in order to address it, you need to be able to have a laser beam that's tuned just on that ion. And so that means at least you have to have some kind of, even if you have a single laser source, you need to be able to controllably split it and route it and that kind of thing. The analog in the superconducting case is an RF cable. And the sort of boneheaded way that this is being done now is you send, a signal down an RF cable for every single quantum bit. This is a system, I believe it's 20, maybe it has 50 qubits down here at the bottom. So that means actually there's 100 wires here, 50 going in and 50 coming out. And then we get into this question of how do you isolate that quantum system from the environment. This is now the bottom of a dilution refrigerator, has to sit at 10 millikelvin in order for thermal photons and things not to be messing up the quantum states that you're trying to manipulate. This is all the stuff that you have to impose in order to get that coupling, that controlled coupling, but without the uncontrolled coupling that we want. And even in this case, there's an issue. It's, I think, in some way, the name for it is not correct. They usually call it anomalous non-thermal effects, right? And it's anomalous because, hey, this is in a refrigerator and it's sitting at 10 millikelvin. But when I look at the quantum system and I back out what the effective temperature that it's seeing, it's more like 100 millikelvin. So it's 1 or 2 orders of magnitude larger than the temperature. And so that's an anomaly. Well, the anomaly is you have this cable, you have 100 cables from room temperature going down there and blasting the thing. And you did your best so that whatever got through was a little bit. But it turns out there's similar effects with the ion traps and so on. The anomaly there is that lattice, that crystal lattice that you make of the ions floating there, they anomalously heat up. You put it in the ground state, you cool it with a laser, and then you watch, and over time it starts, and then ions start flying out of the system. All right. The other big sort of requirement here, well beyond whatever you choose for the quantum system, is how you are going to control this with classical electronics or classical resources. And this comes down to this requirement I mentioned earlier about error correction. Essentially, there's a cycle. You measure the quantum system that projects it into a well-defined classical state. That tells you something. This error correction thing is you divide your system up into 2 parts. There's the part that I'm going to keep quantum and not mess with. And then there's the other part that I made specific interactions, all quantum mechanical, so that these things are entangled with what's going on here. And I can measure those. And in measuring those, I learn about what happened in this quantum space that I didn't want to touch. And I know I should, in principle, be able to learn what I need to do in order to correct the error that occurred. But this requires constant measurement of at least part of that quantum computer that I built. If that was all that was required, it wouldn't be that big a deal. But I have to figure out from that measurement what caused it. What was the actual root cause, the error that occurred in my quantum computer that caused that error bit to be flipped? So it's like I have the the best case would be I've got a table of possible errors. I'd like that table of possible error codes not to grow faster than, excuse me, faster than I can look them up. But that's exactly the problem you have. So you have errors happening, at some fast rate. You can make more complicated error codes that'll correct more errors. So then the question is, how big is that table of possible errors growing, and what kind of computation do I need to do to figure out which one of those things is the correct correction? And then, so let's say I can do that. Now I have to synthesize the signal. All these are fundamentally oscillating signals. They're going to be operating at gigahertz or above typically. So I need to make that decision, synthesize the response, send it in, all faster than those native error processes are happening. This is just showing visually what I was talking about. So here's a representation of this idea of quantum error correction. So you have each one of these is supposed to be a qubit. You have some encoding process, which is you do some operations on the system in this huge quantum Hilbert space that encodes the information you want. You do your quantum computation stuff, and now you have to go and see what the errors were and correct them before you go and do a next step, before the next clock cycle of your computer. So in some sense, it's pretty analogous to if, let's say you've got a 5 gigahertz processor. Every 20th of a or 200th of a nanosecond, I have to step in, check for errors, make a decision about, right? If I really wanted a clock rate of 5 gigahertz, I need to do an error correction step after every single operation, which is currently what it looks like you need to do. You get some idea of the constraint on this. And then, oh, by the way, I'm going to do this with classical electronics, which are already sort of burning out if I try to do something operate natively above a few gigahertz. This is where this circle closes again in terms of that original choice I made for that quantum system. Maybe I do want something that's more isolated, that's going to have a slower decay time, so I have more time to figure out what went wrong. And so I could potentially store my quantum information in something that with a longer lifetime. And roughly, that's one of the big differences between the superconducting systems and the ion traps. The ion traps, it takes 2 to 3 orders of magnitude longer to do an operation on one of them. They also last 2 to 3 orders of magnitude longer. And so from a control perspective, that looks like a good deal. The only problem is if you look at, well, now what's the time to do a computation? What's my clock rate? And it's back to, it's back to the Z80. I have to, my clock rate is painful relative to what I would like it to be, which means that I need more resources to justify in terms of the quantum resources in order to justify the fact that I'm now doing this with a quantum computer and I'm going to use it to beat something else. All right, I think we're doing good. So we're in the final stretch here. This is, I guess I didn't call it out, but there's a few kind of nice references throughout this. A lot of them are Wikipedia, frankly. So, if you're interested, it's pretty easy to find information. But this is a really nice review article if you want to delve into sort of where things are at and what some relatively smart people think about the prospects for improving this. So there's this report from the National Academy of Sciences. And they kind of have this roadmap of, well, this is what you need, different sort of, I don't know if you guys can, no, great, you can't see it. Okay, so that's the VGA thing. You need, it kind of amounts to, hey, first we need 10 qubits, then we need 100, and after that we need 1,000. But it also comes into each of those steps, well, we're going to correct errors faster than they happen, and so on. This is also a useful plot of the error rate versus the, so this is on this axis, this number of qubits. this is the error per operation. And so this is the domain where all systems that currently exist lie. These are roughly the thresholds that you need to cross in order to have to be able to correct errors faster than they're occurring. So that's 1, 2, 3 orders of magnitude away. Not too bad. Because the thing that gets people worked up about this is if you look at the rate of error, the rate that systems are improving. So I just made my qubit this year better than last year. It does fit on a log-log kind of scale, roughly, if you're looking at single qubits. If you start looking at 2-qubit gates, then it's a little worse. If you look at 2-qubit gates in a system that has more than 2 qubits, it gets significantly worse. But the argument is that there is pretty reasonable evidence, heuristic evidence, that we are doing better at this job. So we're rapidly potentially approaching this kind of point where you could do this in a scalable way. One way that people talk about this is, which I think is, it's kind of a fun way to say it. It's a little overblown, but you can say the rate here is the double exponential. If you really are improving the system performance at an exponential rate, some kind of analog of Moore's law, then, and the computational power, though, is also scaling exponentially with, say, the number of elements, then nominally you could argue that I'm going to wake up tomorrow and there's going to be a quantum computer and the whole world will be completely changed, because that's sort of the nature of exponentiating twice. I think there's a little bit of feedback between those two exponentials, so, but it's a fun thing to think about. So where are we at now, and like what if you want to say you want to play with a quantum computer that's already built, where can you find one? There's a few resources out there now. I think the easiest one to access is actually this IBM Quantum Experience. Has anyone played with that or checked it out? So a few of you. It's fun just to go to the website. Go into Google, IBM Quantum Experience, and you'll see a lot of tutorials. You can write quantum programs and either run them on a virtual machine or actually run it on their physical test bed, and you can see the big difference between simulation and reality in that case. And that's where you get to this kind of number. So they have systems now between 6 and 20 qubits that you can log in and play with. The number of effective qubits is still around 6, which is to say, suppose I want to do something on this qubit and that qubit and that qubit, and then I'm counting up the ones that I want to involve. I get up to about 6 and I can do it. If I go to 7, then I lost one. So the effective number of qubits isn't quite the same as the number that's written there. Rigetti is another resource there, local. And both of these have really nice APIs. You can write Python code to basically access the quantum computer and either simulate it or run it on the real system. By the way, I think end of September we're hosting a workshop with Rigetti here at the lab that's going to be kind of a follow-on to this series where they'll go over quantum algorithms. Then we'll have like a hackathon at the end. It's going to be a week-long thing where you can learn how to write quantum code and then try it out. So hopefully that'll be kind of fun. Google is also doing a lot in this space. They don't currently have public access. There's press releases that say how many qubits there are, but you don't know, how many effective there are and things like that. Another thing that's ongoing is DOE has invested pretty heavily in the last couple of years, especially in this. They set up 2 what should become user facilities. This was the first year they're in operation, so there are no users yet. But both LBL and Sandia have testbed systems. LBL has a superconducting system, and Sandia has an ion trap system. And those should be available probably by proposal, kind of like a beamline kind of model. You say, I want to do this experiment, and you'll be able to go on it. Then the other sort of sole system that's available potentially on the commercial space is this ion Q thing. One cool thing about this is they have an 11 qubit system. It's about 11 qubits, which is kind of cool. So in fact, that's in my current, I could be a little off, but it's about the best quantum computer we have right now in terms of number of operations you can do without error and the size of the space you can do them on. So that's it. That's my conclusion is, hey, this is tough. And all this stuff sort of comes together. You can't just choose your quantum system as and then ignore everything else and vice versa. And the performance of your quantum computer really has a lot less to do with what you use to store your quantum information than how you're accessing it and controlling it. So, thanks.
Thank you.